Ultrasound needs very high frequency vibrations. In order to generate these vibrations, you need something called a piezoelectric crystal. Piezoelectricity is caused by the chemical composition of the crystals inside the material. In this case, we can consider quartz, silicon oxide, and its ionic bonding means that there is distributions of charges in positive and negative areas. And these charges are kind of flexible, so you can squeeze them and push them around a little bit. And depending on what's going on externally, they can redistribute slightly. Be it a push or a pull, you can squeeze the crystal, or you can put a positive and negative potential on either side in order to force the crystals to shuffle around. So yes, the reason for piezoelectricity is a chemistry thing, and so you don't need to worry about it too much. But those of you who are chemists might be able to understand a little bit of what's going on. A good way to visualize these positive and negative charges in the compounds are as dipoles. Dipoles are representations. We can draw them like a little circle with an arrow, okay, and add a little plus and minus, which shows their positive and negative distribution. If we look at a crystal that has nothing going on whatsoever, those positive and negative distributions, the arrows or the dipoles, are randomly distributed all over the place. So there's nothing really going on because they tend to just cancel each other out. However, if you were to put a voltage across a piezoelectric material, so a positive charge on one side and a negative charge on the other, what you would end up doing is forcing those dipoles to realign. And if you were to get all the positive dipoles, or the positive parts of the dipole in one of those crystals to all repel from this side here, so turn and spin away, what you'll find is that the crystal ends up squeezing together in order to get away from the positive and the negative. So these dipoles, you can almost imagine the positive side of them are all trying to squeeze away, and the negative are all trying to squeeze away. So the whole crystal contracts. Similarly, if you were to put a negative and a positive charge on either side, reverse it now, then you would get a shift, a redistribution of those piezoelectric dipoles, but this time they would pull towards the terminals that are attracting. Okay, so what you would get was a slight expansion of the crystal. So the piezoelectric effect causes crystal materials like quartz to generate either an electric charge when the crystal is being compressed. Now that's not what we're talking about here. That's something different. We're talking about the reverse. As the crystal material compresses or expands when an electric voltage is applied. Okay, so you can get a crystal to vibrate. Because if you change this positive and negative terminal continuously, even 20,000 times a second, you can get the crystal to vibrate, to contract and expand 20,000 times per second. So you generate a vibration, which is at an ultrasound frequency. Now the ultrasound is generated by a little object called a transducer. It's got a metal outer casing, acoustic insulator so that the sound is directed through the front, the plastic nose. And at the front you also have electrodes that apply an alternating potential difference. That means that regularly, at depending on the frequency that you want, but many times per second, the potential difference across the terminals will swap. and there you have your piezoelectric crystals. If we have a closer look at that, these are all your tiny little circuits. Okay, and each one of these contains many layers of these vibrating crystals, which would then add to each other and add to the effect and produce a strong ultrasound frequency signal.